Okay, yeah, so today we're going to go over tips and tricks of training neural networks. Pretty much last week, you learned how to train basic neural networks. This week, we'll go over some best practices and other tools you can have to train your neural networks and have them do really well. So really quick on the agenda. Okay, first up, I don't know why the font is like shadowed. I think that looks terrible. But on the agenda, we'll review neural networks really quick. Then we'll go over some loss functions that you should probably see, I guess, as part of your training. And then we'll go over some tips and concepts for under and overfitting, and just some I guess just generic tips and tricks you should probably know, and problems with neural networks you can deal with. Okay. So first up, I guess, just to recap neural networks, you have, I guess you're training them by taking this gradient with respect to like a part of your training set, and you're moving all your weights in the direction of steepest descent or descent. And so you're trying to minimize your loss function. You when you apply gradient to apply gradient descent, you sort of find the gradient at the very last node and back propagate and find the gradient in all the previous nodes, which is called back propagation. And you take a step in that small direction of the gradient, and you repeat this until the gradient is 0, until which you can't take any more steps. And yeah, to train efficiently, pretty much you don't have to compute your model across the entire training set. Instead, you can use a sample for each iteration. Pretty much you'll be taking 32, 64, somewhere around that number around data points, and computing your derivative on them, instead of taking all your maybe all your thousands of points in your training set. And this will allow you to train faster and also have some sort of noise pushing you left to right, which will make your model, which will help your model converge to a global minima, because having that having the random noise push you left and right might be able to push you out of a saddle point. So if you have I don't have an Apple Pencil, but if you have a saddle point, whoops, that's a bad saddle point. If it's flat here, but you're stuck here, gradient 0, but you're this is obviously not the best you can do. If you have some noise pushing you left and right, as you would with the case of taking this sample of your entire data set, you might be able to get pushed down out of this saddle point and into the global minima. So yeah, that's pretty neat. Not sure if Praveen went over this, but you should definitely know this and the motivation behind it. Yeah, in practice, it also saves a lot of your compute, since you only need to do only need to predict on 32 images instead of 32 points instead of your entire set. So activation functions, I think, yeah, just to quickly recap, it adds nonlinearity into your model. So if you just have linear layers, I think if you just put 5 linear layers and no activation function between them, is going to be the same as putting 1 linear layer, because you can just multiply all those matrices and they'll cancel out. Actually putting activation functions is going to make your model nonlinear. And I think you can prove that with a deep enough network and enough activation functions, you can model any nonlinear function, which means sort of in real life, most of the time we try to, when we're predicting something, we're predicting something nonlinear. And yeah, I guess this makes neural networks pretty neat, because it just means that they can model anything. Yeah, ReLU, I guess, is the most commonly used in neural networks in the middle, or in the middle layers, I guess, just because it has really good properties, because there's the gradient above 0 is always 1, and well, it doesn't it doesn't go to zero, even when the numbers are really big. And it has non-linearity. However, one problem you might have is that the gradient for values below zero is zero. So if like, you can imagine like if one neuron is always outputting like, shit, Mayhildren. Okay, well, you can imagine if for ReLU, you can imagine if one neuron is always getting like a really negative value, the derivative of it is always going to be zero. So it's never going to train. And that becomes a problem because like if your neurons don't train, your model doesn't get better. So that's called the dead ReLU problem. And it can be pretty bad. And I think like studies have been done on this. I'm not sure if I can give you a number, but like a good amount of like neurons in a deep network are dead after like some training. Oh shit. Um, so I guess one way to like fix that is to add this sort of nonlinear portion with using LU or any other like modification on ReLU, adding a nonlinear portion that has some derivative below zero, and that in practice like helps fix it. tanh is another like pretty popular activation function. I don't think it's used for anything specific unless I'm like wrong about this. But yeah, that's pretty good. And sigmoid is exactly like tanh, except it's scaled to be between 0 and 1, and its value at 0 is 0.5. And like you saw already, this is basically used to output a probability. So if you want to detect between cats and dogs, if you put sigmoid at the very end of your layer, your model, you can interpret your model to output a probability between 0 and 1 that this image is a cat. And another loss function that you should probably know is for multi-class classification. You should know softmax activation, which is going to sort of output a probability for multiple values, is going to scale them up such that they output probabilities of each class. So it's going to scale it such that the sum of all values is 1, and that each value is like a probability that it's this class. So for 10 classes, if you output like 0.9 and 0.11111 for all the rest, you're gonna have like probability that is class 1 would be 90% from your model. I need some water. I'll be right back. Okay, hopefully you had enough time to look at this beautiful slide. So there are many different loss functions you use in practice. And I guess you should always try to like fit a loss function as best as you can to your problem, because what it measures how like bad your model is or how like incorrect your predictions are. The two like very classic like standard ones you should know is L1 and L2 loss, which is like a mean square error and mean absolute error. They're the most like sort of standard loss functions you can probably use for any problem. And slight difference between them is that the outliers are affected differently. For mean squared error, since you're squaring your terms, the outliers are going to be more important, or like going to contribute to your model a lot more. Another of the loss you use for probability estimations, it's called cross entropy. And pretty much what it does is it assumes that your values are between 0 and 1, and not actually 1 or not actually 0. So like between 0 and 1 exclusively. And it basically scales your loss such that in this graph, in the graph below, you can see that this when the true label is 1, the loss is going to like exponentially increase as you go towards 0. So this is like, you should use cross entropy loss whenever you train a probability or like probabilistic model or classification model, like on like a classification task. And yeah, pretty much any differentiable function there is appropriate. One thing like we've worked in the past with before is using SSIM, which is in the bottom right. It stands for like structural similarity, um, something, imaging constant or something. But pretty much it like gives you a much better representation of how similar your image is to your like true label. In this little graphic, the point in the middle is your reference image, and all the points around the circle have the same mean squared error value. So like according to mean squared error, all of these images are equally as bad. However, like I think at least to me, it looks like the image on the bottom right is much worse than the image in the top left. And this is pretty much because like the image in the top left is just like scaled up, and it's made brighter by some constant, which mean squared error tells you that it's wrong. However, when you look at the distribution, which is what actually SSM does, when you look at the distribution, they're actually pretty similar. So SSM just allows you to get a much clearer view of like how incorrect like image data is, or like how incorrect your image predictions are. Yeah, pretty neat trick. Okay, yeah, for actual tricks, normalizing your features is extremely important. It's like in practice, sometimes if you don't normalize your features, like nothing's going to work. Especially like if they're really bad. Like some features are between like some features in the thousands. Like that's just it just doesn't work because activation functions are centered around 0. And as you can see, like when you feed in values more than like 6, the gradient becomes 0. So if your like data set consisted of values around 1,000, then like just nothing would work because the gradient would always be 0. And yeah, so also normalizing, I guess, means dividing by the mean, and subtracting the mean and dividing by the standard deviation. And pretty much it means that like your outliers are not going to be more than like 6 standard deviations away. So that's going to like work really well for the softmax activation, since even at like 6 is pretty much where it becomes like where the derivative becomes 0. And so your model is just going to your model is just going to converge along. Your model is just going to converge a lot better and have much better performance. Also in gradient descent, so this like the graph in the top right of this diagram is sort of a way of interpreting how your model trains. So you're given like these rings represent like your loss, and the bluer the color, the less your loss is. So you should like, and the x and y the x and y axes represent your model weights or model parameters. So you can see that there's like a minimum of loss at the center, and the goal of gradient descent is get to that center. However, when your like features are unscaled, it might be like very unstable and take a lot longer to converge. And also like your loss is going to go up and down a lot as opposed to scale. And like I said, if your features are like, if your data set is like in the thousands, like it's just not going to work. Okay. So underfitting and overfitting. This is more of a concept that you should definitely know. It's really important. So pretty much since like in the last slide, we talked about neural networks being able to model any arbitrary functions. They can pretty much like, if you have this training data, right, they're able to, with enough like layers, they're able to like memorize, they're able to sort of learn all the points and be able to get like 100% accuracy or 0 loss if a model like is deep enough for some arbitrary data set. And that's not exactly what you really want. So overfitting is when your model fits to your training data too well and loses the generalization, like to test data. And the underfitting is when your model is too simple to sort of to even fit to the training data. So I guess if we go from left to right, underfitting might happen if you like your model is just linear regression. A linear regression is obviously not able to fit to like a lot of different functions, and it's not going to do well. Having an appropriate fit would sort of look like the middle graph here, and it looks like a very solid like decision boundary between these points, even though it does make some mistakes. And the overfitting is pretty much drawing this like squiggly line that traces out like all the points perfectly, such that your like model, your model did what you told it to do. Like it it minimized the loss, but at this point, like you really didn't want it to minimize it this far, because now you just have this weird squiggly line going through your data. And if you were to apply this like on like more data points, save this x is actually just save the x in the middle that's like surrounded by this like a squiggly loop. I'll annotate. Say the squiggly x is actually just an outlier, and it's going to be like in another data set is going to be a 0, or like in your real world there might be a 0 there. Well, your model is going to like get a bunch of errors in that region, and you'll see that you'll see that your test accuracy actually starts decreasing at some point. So from like the diagram on the top right, I guess there's as you're training your model, first you sort of you're teaching it to fit on the training set, and your test error is also going down since it's able to generalize some knowledge to accurately predict your test set. And at some point, there's going to be like this elbow for the test error, which is going to be your best fit and sort of the best error you can get with that model on your test data set. And after this point, even though you're still going to keep training, you might you might not be at the global minima. Like you might still be able to decrease your loss further ahead. But even though like you keep training, the test error is now actually just going to go up instead of decreasing, because you're drawing this like super squiggly line through your training set, which is not representative of your test set or the real world. Okay, so now that we have this problem with like models being too complex, or like you're training them too well, how can we tackle it? Well, there's a couple of techniques. So first up is L1 and L2 regularization. I guess first thing you might notice is that L1 and L2 is also the name of loss functions. You're gonna be like, why is it the same name? And it's because that it's you're taking the absolute value or squaring your weights. Pretty much, if we force, the main idea of regularization is that if we only force the network to use necessary features, it'll avoid overfitting. So if you you make it like dumber by limiting something, it's only going to it's not going to overfit if you make it really dumb. But if you make it really dumb, it might not be able to learn anything. So it is like kind of a trade-off. But what L1 and L2 regularization do specifically is that they add to your loss function, or to your cost function, as you have the loss, which we already seen in previous lectures. But now you're adding this another term, which is in this case the L2 regularization term, because it loops over every weight. So I don't know what M is, but I think it looks at every weight in your neural network, and it squares it and sums it up. So if your neural network has like 10 weights, it's going to get like the squared sum of all of these weights, multiply the sum by a parameter lambda, which is a hyperparameter. I'll just write HP and add it to your loss function. So now, like you're defining your cost to be not only like how well your model does predicting, but also how few weights it's able to use, how like small its weights are. Is like if you have small weights, it become like you tell the model that it's better to have small weights. And it has this and the regularization term is usually scaled by an alpha. In this case, it's a lambda, but usually it's an alpha. It's just like different variable name.
Wait, so does the what do you call it? The gradient descent, the it's the derivative. Do we take the regularization term in the derivative as well?
Yeah. So you're going to take the derivative or gradient of the cost, and that also takes the like derivative of this. That's a good question. Wait, also I just realized I didn't ask for question. I didn't pause for questions. Do you guys have any questions about any slides before or include or this one? All right, sounds good. Yeah, so we'll just keep going. I hope like the motivation for this. Oh, I guess I can clear up some motivation. If your weight is 0, so your weights like your if this is your weight, right, and this is going to be sort of the regularization term. Your weight has a minimum as like the regularization term has a minimum of 0, and if your weight for a specific feature is 0, you're not extracting any information from it. So if you multiply, if we go back a bunch of slides, um, you'll see that sort of what for this if this neuron multiplies some if this neuron, this is like the input, if this neuron multiplies some feature by 0, it does this like inside of it does the sum of weight times the feature times the input. And if this weight is 0, then this x is not contributing to the decision of this neuron. So if your weights like go to 0, you're considering less features from your previous layer. And so that's why like I guess we say that if we like don't look at too many features, your model is going to be simpler. And the way we don't look at too many features is by setting the weight to 0, such that this one term, it doesn't contribute to this to the actual activation of this neuron. So for example, like if you have x1 um, and it's multiplied by w1, which is 0, like this x1 is going to be not used for this neuron. Okay. So like we already, I guess this is one way of combating regularization, is by adding this like pretty tricky term and changing the way you like use gradient descent, I guess. Another way is you just like instead of changing the like weights instead of penalizing weights, we just randomly remove features. So, and this technique is called dropout. Pretty much at any point, during like forward propagation, you add another layer called the dropout layer, and the dropout layer is specified by some probability. And when you're doing your during training, when you're predicting your output, you're going to have four of these, like four hidden like neurons output something, and then they're going to be passed into the dropout layer. And the dropout layer is just gonna, with a probability of 0, with a specified probability, is just gonna set these to null. So for example, like in one pass, it might just drop these features or set them to 0. Um, so instead of decreasing your weights such that some features go to 0, such that some features like are not impacted on the neural on your output, what dropout does is it adds this layer which just kills information. Like like during training, you're just like randomly like deleting information from your system. And you might like think, oh, that's kind of dumb. It's like that's I don't know. I first thought it was like hella dumb, but it turns out that if we just randomly remove these features, your network actually needs to rely on all the neurons independently to get a good prediction. So, and what that means is like if we have 4 of these inputs and we just like at some point we killed 2 of them, well, your model still has to do like it's still gonna try to predict well. If it doesn't predict well, it's gonna get trained to predict well. And so there's gonna be 2 of these features are gonna try to like your model is going to try to get a good prediction on 2 of these features. And what that means is like your model needs to be able to have a good prediction on any like combination of these features. Like the first 2, the last 2, the middle 2. It needs to be able to get like a solid prediction no matter which features get dropped. So this is why you sort of like this is why we say like independently of others, is because like if some feature gets dropped, your network still has to get a good prediction. So it cannot rely on just the first node to get a good prediction. And yeah, you can say that each neuron in deep layers becomes a good signal for the input, which means that like it's a it becomes like a good metric for predicting the output. Sorry. Um, well, you might like say that you might ask, how does this actually sort of stop our model from overfitting? And uh, I think my like understanding of it is that if you have if each sort of neuron is good at predicting output by itself, that's sort of similar to just having one of them, just having one neuron instead of all 4 of these. And that like this neuron with like a really high probability, if your dropout is really high, you're only going to have like one neuron at a time. And so each of like all the neurons might learn to be the same thing. And so your model is artificially going to be like dumber. It's going to be the same as like having 4 of these. Oh my God, this is going to take a while to draw. It's going to be the same as having 4 of these and just having all of them feed into one. And that'll like, and then it'll go into the output. So that's like if your dropout is really high. And yeah, so dropout is really high. Like you made your model pretty much have one neuron essentially, because you like all of them get killed during training, and that just made it dumber. And so now like maybe when you put all 4 of these back, your model like is not going to be much smarter, since all of these features are going to be uh, about the same for like a really high dropout. And like in practice, you don't use dropout like 0.8, you use a dropout percentage of about like 0.2 or 0.1, and it's going to have like overall similar effect, but just not as like drastic as having one neuron. It might be equivalent to using like a couple neurons, and this way you're able to train a bigger network, but not have it like overfit as much. Do you guys have any questions on this?
Yeah, question. Let's say we have a regression problem, right? And we start using dropouts. And so now this dropout basically happens during the training phase, right?
Yeah.
Okay. So when we're training, it's like we're missing 10% of our weights, 10% of our, whatever we're getting, right?
Yeah. Yeah.
So when we're working with regression, and if we're training with 10% less information than we will eventually, wouldn't our regression output be 10% lesser in magnitude as well?
Mm. I mean that makes sense. Um,
So what do we
I
do for
think
that?
yeah, I guess a really good question. I think that's a really good question. I think when you have 10%, like there's a chance that all of your networks, okay, that's not a good argument. Um, so in practice, I guess one thing you do is you normalize your like after dropout, or I'm not okay. This is a question from the notebook, but after dropout, you're going to also normalize. So even if it's 10% smaller, that's not going to that's not going to affect it because you normalize each batch. Um, like by itself, I think you're like, I think you're like that point is really correct. I don't know the answer like to without using normalization. I don't know like the answer to that. Yeah, I think definitely like look it up. I'm sure it's like, I'm sure someone's answered that.
Cool.
Yeah, sorry. Okay, yeah. Any more questions?
Yeah, so one quick clarification is it doesn't drop out when you actually are predicting with it, or does it
Yeah,
also
yeah.
predict?
It doesn't.
Okay, all right.
Yeah, it's only doing training, and yeah. Okay, I'm moving on. So now batch norm. The slide looks a little more dense. Okay, so uh, one, and this is not necessarily, this regularization method is not as like strong or as yeah, I guess as strong as others. It's more of like a way of it. This this sort of method is also just going to make your model a lot better overall, instead of just like regularizing it. And what it means is what like normalization or batch norm does is you're adding this layer, and in the presentation it doesn't look like a separate layer, but in PyTorch it is a separate layer. And so you're adding this layer, which the point of which is to learn the mean and variance. The purpose of this layer is to learn the mean and variance of the outputs of this neural network, of this layer. And after it, like while it's learning that, it also normalizes its inputs to this learned mean and variance, or like it normalizes by this mean and variance. So it subtracts your learned mean, and it subtracts and it divides by your learned variance. And what it does is essentially like, since you're applying this to every output, it limits the amount of variance you have in deeper layers. What that is, because like even a large like something like a large input will be normalized to like normalized by this learned like mean and standard deviation, and by reducing this variance in neural networks overall is going to mean that like you're not going to have this like super squiggly decision boundary, because a lot of the time the way you get like the squiggly decision boundary is by having like really high values in your features. So if you have like really high values in your features, you're able to get like you're able to so if you fit like an x to the 7 polynomial, this x to the 7 value is going to be really large, but there might be like other x to the 6 and x to the 5 values that are also like really large, and that is allows you, like those really large values allow you to fit like this overfitted like line. But by using pretty much by like normalizing it, it means that every feature is going to be scaled down, and is not going to have like as large of an impact on your final output. So another like key part is that having like some delta, or sorry, having some like small change in your input, having some small change in your input is not going to like affect the neural network that much. And that's really good, because you don't want like you don't want if you're training like an image classifier and you're like, wow, this is like, and you're looking at a cow like very clearly, but then like a bird flies into the like camera, and it's like the bird doesn't have to do anything with the cow. The cow's still there, but it's like some small input that somehow gets like amplified in these middle layers. Somehow gets amplified in these middle layers and causes your model to like change very drastically. And then your model is gonna say like giraffe, because maybe the bird was on top of the cow and it looked like a giraffe. And like that's just not good. So yeah, pretty much normalizing all the features, normalizing all your like neuron outputs in the middle layers is going to reduce variance, because a small change in your input is not going to affect the output as much. Yeah, and this is sort of like another way of regularization, because you're like you're avoiding really high like values, and you keep scaling them down to be like mean 0 and variance 1. Does anyone have any questions?
So are the mean and variance for the entire like layers outputs or just that neuron's outputs?
It's just the neuron.
Okay, cool.
Yeah, and that's like you're also like learning. You'll see that like the background layer has its own mean, and has like a variance for every like it's learning these two values for every input. So if your input's like 128, the batch number is gonna have 256 parameters that it tries to learn, and it like learns it for each neuron. Also, there's like while training, you're changing these mean and variance, but when you're actually predicting, you should not change them. And there's a training and test mode, or prediction, like training and inference modes for this layer. And I think like so in some network, in some frameworks, in some like coding stuff, you have to like explicitly set it to train to like inference mode, or else your accuracy is going to be really bad. So yeah, watch out for that. Okay, now we're done with, those are all the ways I guess I included to tackle overfitting, underfitting. Yeah, these are like, those 3 ways are the ways, like most common ways people tackle under and overfitting, not under, but overfitting. Now we're going to talk about like using different optimizers and learning rates. So first up is I wanted to like show you that learning rate is really important. Pretty much like this is like, these points are, I guess, represent like a model converging to a nice like loss minimum in this like valley. And what it does is it takes this point and sees that the gradient is this way, and it changes the weights, changes the parameter to here, and computes this like next loss, and then changes it to here, changes it to here, changes it to here, right? And your learning rate is like some value that scales how far you change it. And so now, if your learning rate is too high, we can imagine like what actually happens is that it sees that the gradient, like it sees that it should change it in this direction, but what it does is it changes it all the way here, and it lands on this point, and then like it might change it on the next step, it might change it like all the way here and land like on this step. And so, this is still going to minimize, right? Like, even though it looks kind of sus, it's still probably going to work. But if your learning rate is like too high, let me extend this graph. If your learning is too high, it actually is going to jump here and go, and your loss is going to now be this. So you can see how that's a really big problem, because you're unlearning the model. You're making like, that's just bad. And next up, next up is gonna go like all the way here. And so you're pretty much increasing your loss. You're ascending instead of descending. And to like draw it better on this is going to be like doing this little spiral. Or if we connect the lines, is going to be sort of going this direction out of this optima instead of actually instead of in, you're going out, and you don't want to do that. So that's like why learning rate is really important. And you might ask like, oh, why don't we just set it to like be really small? But the trade-off for that is it's gonna be a turtle and just like take like 10 years to actually optimize. And we don't have 10 years. So yeah, that's pretty much learning rate. You can, in practice, since learning rate is a hyperparameter, which means you set it before training and you sort of can't really modify it during, or well, there are ways that there are some people modify it, but you're pretty much just you're specifying the learning rate like at the start. And what you can do is you can just like choose different learning rates of like 1, 0.1, 0.001, 0.00001, and see which one works better, and then just choose one of those. Usually, like you're not gonna have a significant difference between like 0.4 and 0.5. Those are gonna be about the same. Like the difference is really like in magnitude. It's when you have like 10 to the -3 versus 10 to the -1. Like those are like those are like the big deciders. Okay, so now what if like stochastic gradient descent, although, it's pretty good, I might still get stuck on this saddle point if the saddle point is like too large. So maybe it's just gonna bounce around inside this saddle point, even though it adds this noise, it might just bounce around the saddle point and never, reach this valley. So what if there are some ways to improve that. And first up is like, if we imagine sort of this valley, let me draw a better one. If we imagine this like hill and we're doing gradient descent, but you get stuck here, although you wanted to actually go here. Well, you can imagine sort of doing this as rolling a ball down a hill. The ball at this point, like isn't gonna get pushed forward, right? Like there's nothing really pushing it, but it's already rolling down the hill. So it's just gonna keep going. Like the ball doesn't care about this little saddle point. And so we want to be like the ball. Our model wants to like not care about these saddle points. And so what we do is we can add momentum to our changes. And this GIF is actually not working. So I can't show you, but pretty much like adding momentum is going to allow you to escape out of this little saddle point and just keep rolling down the hill until you reach the bottom. And another like crazy thing that momentum might do is you might have this little hill, you might have like something like this, and we can imagine like you're gonna roll a ball from here, it's gonna roll over, it's crazy. One like negative thing is if this is just like a valley, your ball might like roll up and then down and then up and then down and then down, but it's still, in the end, it ends up in this point, and you can prove that it ends at the, your ball. You can roll a ball down this hill and you'll see that it rolls like ends up at the bottom. And yeah, our balls are also going to end up at the bottom. That's so we covered stochastic gradient descent. What I just described is momentum. This is some wacky, like crazy math that ends up being better than the previous two, but it does so by adding like, I think it adds like just additional complexity. At some point, I think it is that like you can definitely learn these at some, like it's just I didn't want to like go over it in presentation because you can probably do this on your own. If you wanted to, it's not really necessary. The ideas behind all of them are pretty interesting. But in practice, like, or sorry, for purposes of this workshop, I just wanted to cover momentum because that's like a really big improvement to what we have. In practice, you're always gonna want to, or most of the time, you're gonna want to use Atom. Atom Optimizer. You can ask Joey Kraut or Joey Hena about what they do, but I wouldn't expect like being able to understand what they do unless you've taken 189. Because they're pretty advanced, but I think it's like the best in class, pretty much, for like, yeah. Okay, so do you guys have any questions? Okay, I think we're about on time. Then last up is we talked about these hyperparameters, the regularization constant alpha. Whoops. We talked about these hyperparameters that you set, like, oh my God. We talked about these hyperparameters like alpha. We talked about the learning rate, LR. That's LR. How can we, these sort of parameters you specify before training. And like you might ask, well, how do we how do we find the best one? Is usually what you can do is you just do a grid search. So you just do little 2 for loops. You do for alpha, say between like 10 to the 10 squared and 10 to the -2. And same thing for learning rate. You do like this loop and you just do train and evaluate. You, for every possible value, you train your model and then you evaluate to see how well it does. And you just brute force pretty much all the combinations of hyperparameters you want to try. You might be like, oh, I'm pretty smart, so maybe I'll be able to choose like good hyperparameters by myself. That's, you might be pretty smart, but like you can also just set it overnight and sort of like let the brute force do its own thing. And also when you evaluate, sometimes what ends up happening is you need to evaluate like on another data set. So you have your training data set and you have your test data set. But when you're doing this grid search, something that you should ethically do is have another data set called the validation data set to validate, like to do this grid search on. This validation data set is going to allow you to choose a hyperparameter without sort of like overfit, without picking a hyperparameter that works best for your test set. So evaluating on the test set should be the last thing you do. You should not like look for a hyperparameter based on the test set. And I think there are techniques like that find hyperparameters for you. I think overall it's just called AutoML, this sort of field. If you're interested, you can learn more. But I don't know, like there's some motivation for picking like the regularization term, pretty much. For picking this regularization term, the higher it is, the more you're gonna penalize the weights. So the higher it is, the dumber your model is, and the lower it is, the smarter your model is. So if you see that your model is being really dumb, and you suspect that it's this term being like if your model is underfitting, sorry, I'll use like clear terms. If your model is underfitting and you suspect that it's the regularization, you might decrease this parameter. And if your model is overfitting, you might increase this parameter. Okay, and here's another problem in neural networks, is the vanishing gradient problem. pretty much when you have deep networks, way like deeper than this, you like is deep, like is deep. When you have deep networks, you might have a vanishing gradient, because even like for any features, your derivative is going to be like less than 1. And when you do backpropagation, right, you're multiplying the derivatives. You're sort of you're multiplying, this one, you're sort of this derivative, to find this derivative, it multiplies this derivative. And you can prove it mathematically, or you can look up backpropagation online. But pretty much like when you're going back through your network, you're multiplying these derivatives. And when you multiply numbers that are less than 1, the numbers go to 0. And so when the derivative goes to 0, your network stops learning. So if the derivative of like all of these for all of these neurons, if it's 0, these are going to stay static. And that pretty much like that becomes a problem because your model stops learning. And this is more of an interactive slide, but like what techniques that we learned before do you think could help with this problem of if you have like large values, the derivative is 0. So how can you like from previous slides, what is something that like gets rid of these large values down? Scales.
L1 plus L2
Normalizing the field.
regularization.
Batch now?
Wait, sorry. Okay, well, first thing I heard L1 plus L2 regularization.
Yeah,
So
but
I'll go through like each one by one. So L1, L2 regularization, like, it might help, although it doesn't like directly sort of may not directly really like it may not directly help with this problem, because I think there's in chat. Pretty much it doesn't like directly solve this issue. So I think we like from what we talked about, batchnom really does this the best because it makes sure to normalize your features by a variance or standard deviation, such that they're in this sort of area where the derivative is non-zero. But even if the derivative is non-zero, like for these networks, having the derivative is still less than 1. So that's a problem. And although I didn't include this on this slide, what some neural networks do, and I wish I had a pencil to draw this, but you might have like, so you have this neural network and each rectangle is a layer, right? And the layers are connected. So what you might do is you might have something called skip layers, where to this layer, what's fed in is the previous layer plus the layer 2 before. And you might like skip every other node. You might skip every other layer, such that you pretty much have like this. In this one neural network, you actually have another neural network baked in that's only like that skips these 2 middle ones. So you're like essentially you're able to have like a smaller model, and since you're just moving these features through, you're not going to the derivative is actually not going to be like not going to vanish as fast for this smaller neural network. So you'll still have some derivative backpropagate to this. And so this technique is called skip connections, and it allows you to deal with this vanishing gradient problem really well. And that was like, these skip connections were one of the things that allowed you to have really deep models for like computer vision. Chat. Yeah. So I think this is ResNet. Okay, so do you guys have any questions? Sounds good. And last thing is, well, you might say, what if you wanted your model to do really well, but you might not have enough like compute to, you might not have the time or like compute to train your own model. And so what if you wanted your model to do really well, like as good as anyone else? What if like you wanted to get as good as performance as anyone else with just one line? Well, you can just copy and paste someone else's model into your code by pretty much by using transfer learning. Is you just import someone else's model. And then you have it like you have this guarantee that is going to do really well on this task. And so so far it doesn't really sound like transfer learning. It sounds just like copy and paste. But what you can do is if you, for example, wanted to, instead of classifying, if you wanted to draw a bounding box, so instead of like classifying between car and bicycle, you wanted to do some other task, maybe also specify the color of the car and or the bicycle. Is what you can do is you can pretty much like take the first like layers of the model and throw the rest of these out, and then you add your own ones. You add your own blank ones that give you whatever output you want. Do another task like color plus what is the object plus the color, and then you just train. All you do is train this little sub network. So the motivation for this is that pretty much for like computer vision, these layers are going to be like generic features. They're not going to be it's not going to be necessarily task specific. It might have like these layers might have an idea of like what is the overall shape of the object. And it's this idea that the deeper you go, the more complicated the features you build are. So somewhere in the middle, you're going to have like you're going to detect like edges and textures, but not necessarily detect objects. And so you're able to use like this really well-trained model that does really well on this task. So it has good like middle features. And because it has good middle features, you can use the first like whatever layers of this model and then only train this little network and still get really good performance on your task. And so this is called transfer learning because you're transferring a model like from one task to another or from one data set to another without like and you're learning. Transfer learning, makes sense. Okay. Any questions on this? Okay, sounds good. And the last slide, pretty much. So all of this is really math intensive. There's a lot of math going on. Turns out like the way we do this math is all in matrices, and turns out we want to be able to compute these matrices really quickly, and the part of the machine that does this, the part of our computer that does this, is the GPU. So we can actually just use the GPU directly to train our model, which is going to be a lot faster than using your CPU. And the reason why GPUs are really good at computing matrices is because they render graphics, which is essentially the same thing. I think, I don't know, I've heard it's the same thing, but we use this GPU to, instead of a CPU, to get like much quicker performance, probably like 10x at least performance, like train things at least like 10 times as fast. And what you need to know is that NVIDIA has CUDA, which is sort of like, which allows you to use like a GPU really easily to for training. And it's integrated both with PyTorch, which is what we use in our notebooks, and TensorFlow, which is an alternative to make GPU training much easier. And pretty much like on PyTorch just comes down to like a couple of lines that allow you to use a GPU and get this really quick speed up. Okay, so that's the last. Oh, I guess any questions on this? And yeah, that's pretty much that is the last slide in the presentation. So I hope that was interesting. Yeah, now we're gonna go into the notebook. So I'll stop recording.